Tubular function. Learning objectives include describing major sites of reabsorption of solutes in the nephron, describe mechanisms of tubular reabsorption, and describe transport mechanism for absorbed substances, describe renal threshold of glucose. So before moving on to this topic, let's learn some major terms associated with this topic, like Na plus K plus ATPase, also known as the sodium potassium pump. This is a membrane bound enzyme that transports sodium out of the cell in exchange for potassium. It transports 3 sodium ions out for every 2 potassium ions in, thereby creating an electrical potential difference. It is also called an electrogenic pump. Then tubular reabsorption, a term representing the net transport of any substance from the tubular fluid to the interstitial space and blood. Then active transport, the transport of a solute against an electrochemical gradient which requires energy. Then transport maximum, an upper limit to the rate at which most substances are actively reabsorbed or secreted, referred to as a transport maximum. Then renal tubular reabsorption and secretion. As the glomerular filtrate enters the renal tubules, it flows sequentially through the successive parts of the tubule: the proximal tubule, the loop of Henle, the distal tubule, and the connecting tubule, and finally the collecting duct, before it is excreted as urine. All along this course, some substances are selectively reabsorbed from the tubules back into the blood, whereas others are secreted from the blood into the tubular lumen. Eventually, the urine that is formed, and all the substances in the urine represent the sum of 3 basic renal processes: glomerular filtration, tubular reabsorption, and tubular secretion. So urinary excretion is equal to glomerular filtration minus tubular reabsorption plus tubular secretion. For many substances, tubular reabsorption plays a much more important role than secretion in determining the final urinary excretion rate. Therefore, tubular secretion accounts for significant amounts of potassium ions, hydrogen ions, and a few other substances that appear in the urine. So tubular reabsorption is quantitatively large and highly selective. Renal handling of several substances that are all freely filtered in the kidney and reabsorbed at variable rates. The rate at which each of the substances is filtered is calculated as filtration is equal to glomerular filtration rate into plasma concentration. This calculation assumes that the substrate is freely filtered and not bound to plasma proteins. For example, if plasma glucose concentration is 1 gram per liter, the amount of glucose filtered each day is about 180 liter per day into 1 gram per liter for 180 gram per day. Because virtually none of this filtered glucose is normally excreted, the rate of glucose reabsorption is also 180 gram per day. Two things are immediately apparent. First, the process of glomerular filtration and tubular reabsorption are quantitatively large relative to urinary excretion for many substances. The situation means that a small change in glomerular filtration or tubular reabsorption can potentially cause a relatively large change in urinary excretion. For example, a 10% decrease in tubular reabsorption from 178.5 to 160.7 liter per day would increase urine volume from 1.5 to 19.3 liter per day, almost a 13-fold increase, if the glomerular filtration rate or GFR remained constant. In reality, however, changes in tubular reabsorption and glomerular filtration are closely coordinated so that large fluctuations in urinary excretion are avoided. Second, unlike glomerular filtration, which is relatively non-selective, essentially all solutes in the plasma are filtered except the plasma proteins or substances bound to them. Tubular reabsorption is highly selective. Some substances such as glucose and amino acids are almost completely reabsorbed from the tubules, so the urinary excretion rate is essentially zero. Many of the ions in the plasma such as sodium, chloride, and bicarbonate are also highly reabsorbed, but their rates of reabsorption and urinary excretion are variable depending on the needs of the body. Waste products such as urea and creatinine, conversely, are poorly reabsorbed from the tubules and are excreted in relatively large amounts. Therefore, by controlling the reabsorption of different substances, the kidneys regulate the excretion of solutes independently of one another, a capability that is essential for precise control of the body fluid composition. Tubular reabsorption includes passive and active mechanisms. For a substance to be reabsorbed, it must first be transported across the tubular epithelial membrane into the renal interstitial fluid and then through the peritubular capillary membrane back into the blood. Thus, reabsorption of water and solutes include a series of transport steps. Reabsorption across the tubular epithelium into the interstitial fluid includes active or passive transport by the same basic mechanisms discussed in Chapter 4 for transport across the cell membranes of the body. For instance, water and solutes can be transported through the cell membrane like intracellular route or through the space between the cell junctions, paracellular route. Then after absorption across the tubular epithelial cells into the interstitial fluid, water and solutes are transported through the peritubular capillary walls into the blood by ultrafiltration like bulk flow that is mediated by hydrostatic and colloid osmotic forces. The peritubular capillaries behave like the venous ends of most other capillaries because there is a net reabsorptive force that moves the fluid and solutes from the interstitium into the blood. Then active transport. Active transport can move a solute against an electrochemical gradient and require energy derived from metabolism. Transport that is coupled directly to the energy source, such as the hydrolysis of adenosine triphosphate, is termed primary active transport. An example of this mechanism is the sodium-potassium adenosine triphosphate pump that functions throughout most parts of the renal tubule. Transport that is coupled indirectly to an energy source, such as that due to an ion gradient, is referred to as secondary active transport. Reabsorption of glucose by the renal tubule is an example of secondary active transport. Although solutes can be reabsorbed by active or passive mechanisms by the tubule, water is always reabsorbed by a passive, non-active and physical mechanism called osmosis, which means water diffusion from a region of low solute concentration, high water concentration, to one of high solute concentration or low water concentration. So solutes can be transported through epithelial cells or between cells. Renal tubule cells, like other epithelial cells, are held together by tight junctions. Lateral intercellular spaces lie behind tight junctions and separate the epithelial cells of the tubule. Solutes can be reabsorbed or secreted across the cell throughout the transcellular pathway or between the cells by moving across the tight junctions and intercellular spaces by way of paracellular pathway. Sodium is a substance that moves through both routes, although most of the sodium is transported through the transcellular pathway. In some nephron segments, especially the proximal tubule, water is also reabsorbed across the paracellular pathway and substances dissolved in the water, especially potassium, sodium, magnesium and chloride ions, are carried with the reabsorbed fluid between the cells. Not sodium, just potassium, magnesium and chloride ions. Primary active transport through the tubular membrane is linked to hydrolysis of ATP. The special importance of primary active transport is that it can move solute against an electrochemical gradient. The energy for this active transport comes from the hydrolysis of ATP by way of membrane-bound ATPase, which is also a component of the carrier mechanism that binds and moves solutes across the cell membranes. The primary active transporters in the kidney that are known include sodium potassium ATPase, hydrogen ATPase, hydrogen potassium ATPase, and calcium ATPase. A good example of primary active transport system is the reabsorption of sodium ions across the proximal tubular membrane on the basolateral sides of the tubular epithelial cell. The cell membrane has an extensive sodium-potassium ATPase system that hydrolyzes ATP and uses the released energy to transport sodium ions out of the cell into the interstitium. At the same time, potassium is transported from the interstitium to the inside of the cell. The operation of this ion pump maintains low intracellular sodium and high intracellular potassium concentrations and creates a net negative charge of about -70 MV within the cell. This active pumping of sodium out of the cell across the basolateral membranes of the cell favors passive diffusion of sodium across the luminar membrane of the cell from the tubular lumen into the cell. Or for two reasons, there is a concentration gradient favoring sodium diffusion into the cell, which is intracellular sodium concentration is low. The tubular fluid sodium concentration is high and negative -70 MV. Intracellular potential attracts the positive sodium ions from the tubular lumen into the cell. Active reabsorption of sodium by sodium potassium ATPase occurs in most parts of the tubule. In certain parts of the nephron, there is also additional provisions for moving large amounts of sodium into the cell. In the proximal tubule, there is an extensive brush border on the luminal side of the membrane, the side that faces the tubular lumen, that multiplies the surface area so that about 20-fold. There are also carrier proteins that bind protein ions on the luminal surface of the membrane and release them inside the cell, providing facilitated diffusion of sodium through the membrane into the cell. The sodium carrier proteins are also important for secondary active transport or other substances such as glucose and amino acids, as discussed later. Thus, the net reabsorption of sodium ions from the tubular lumen back into the blood involves at least 3 steps. Sodium diffuse across the lumen membrane, also called the apical membrane, into the cell down at an electrochemical gradient established by the sodium-potassium ATPase pump on the basolateral side of the membrane. Sodium is transported across the basolateral membrane against an electrochemical gradient by the sodium-potassium ATPase pump. Sodium, water, and other substances are reabsorbed from the intestinal fluid into the peritubular capillaries by ultrafiltration, a passive process driven by the hydrostatic and colloid osmotic pressure gradients. Secondary active reabsorption through the tubular membrane. In secondary active transport, 2 or more substances interact with a specific membrane protein, a carrier molecule, and are transported together across the membrane. As one of the substances, for example sodium, diffuses down its electrochemical gradient, the energy released is used to drive another substance, for instance glucose, against its electrochemical gradient. The secondary active transport does not require energy directly from ATP or from any other high energy transport sources. Rather, the direct source of energy is that liberated by the simultaneous facilitated diffusion of another transported substance down its own electrochemical gradient. Secondary active transport of glucose and amino acids in the proximal tubule is important. In both instances, specific carrier proteins in the brush border combine with a sodium ion and an amino acid or a glucose molecule at the same time. These transport mechanisms are so effective that they remove virtually all the glucose and amino acids from the tubular lumen. After entry into the cell, glucose and amino acids exist across the basolateral membrane from the diffusion, driven by the high glucose and amino acid concentration in the cell, facilitated by specific transport proteins. Then sodium cotransporters are located on the brush border of the proximal tubular cells and carry glucose into the cell cytoplasm against the concentration gradient. Approximately 90% of filtered glucose is reabsorbed by SGLT2 like sodium glucose cotransporters 2 in the early part of the proximal tubule S1 segment, and then residual 10% is supported by sodium glucose cotransporters 1 in the later segments of the proximal tubule. (10% is transported by sodium glucose cotransporter 1 and later segments of the proximal tubule. On the basolateral side of the membrane, glucose diffuses out of the cell into the interstitial spaces with the help of glucose transporters in the S1 segment and GL2-1 in the latter part, S3 segment of the proximal tubule. Although transport of glucose against a chemical gradient does not directly use ATP, the reabsorption of glucose depends on energy expanded from the primary active sodium-potassium ATPase pump in the basolateral membrane. Because of the activity of this pump, an electrochemical gradient for facilitated diffusion of sodium across the luminal membrane is maintained, and it is this downhill diffusion of sodium to the interior of the cell that provides the energy for the simultaneous uphill transport of glucose across the luminal membrane. Thus, this reabsorption of glucose is referred to as secondary active transport because glucose itself is reabsorbed uphill against a chemical gradient, but it is secondary to primary active transport of sodium. Another important point is that a substance is said to undergo active transport when at least one of the steps in the reabsorption involves primary or secondary active transport, even though other steps in the reabsorption process may be passive. For glucose reabsorption, secondary active transport occurs in the luminal membrane, but passive facilitated diffusion occurs at the basolateral membrane, and passive uptake by bulk flow occurs at the peritubular capillaries. Secondary active secretion into the tubules. Some substances are secreted into the tubules by secondary active transport, which often involve counter-transport of the substance with sodium ions. In counter-transport, the energy liberated from the downhill movement of one of the substances, example sodium ions, enables uphill movement of a second substance in the opposite direction. An example of counter-transport is active secretion of hydrogen ions coupled to sodium reabsorption in the luminal membrane of the proximal tubule. In this case, sodium entry into the cell is coupled with sodium extrusion from the cell by sodium-hydrogen counter-transport. This transport is mediated by a specific protein, sodium-hydrogen exchanger, on the brush border of the luminal membrane. As sodium is carried to the interior of the cell, hydrogen ions are forced upward in the opposite direction into the tubular lumen. The basic principles of primary and secondary active transport are discussed. So, pinocytosis, an active transport mechanism for reabsorption of proteins. Some parts of the tubule, especially the proximate tubule, reabsorb large molecules such as proteins by pinocytosis, a type of endocytosis. In this process, the protein attaches to the brush border of the luminal membrane, and this portion of the membrane then invaginates into the interior of the cell until it is completely pinched off and a vesicle is formed containing the protein. Once inside the cell, the protein is digested into its constituent amino acids, which are reabsorbed through the basolateral membrane into the interstitial fluid. Because pinocytosis requires energy, it is considered a form of active transport. Then transport maximum for substances that are actively reabsorbed. For most substances that are actively reabsorbed or secreted, there is a limit to the rate at which the solute can be transported, which is often referred to as the transport maximum. This limit is due to the saturation of the specific transport systems involved when the amount of solute delivered to the tubule, referred to as tubular load, exceeds the capacity of the carrier proteins and specific enzymes involved in the transport process. The glucose transport system in the proximal tubule is a good example. Normally, measurable glucose does not appear in the urine because essentially all the filtered glucose is reabsorbed in the proximal tubule. However, when the filtered load exceeds the capability of the tubules to reabsorb glucose, urinary excretion of glucose does occur. In an adult human, the transport maximum for glucose averages about 375 mg per minute, whereas the filtered load of glucose is only about 125 mg per minute. GFR into plasma glucose is equal to 125 ml per minute into 1 mg per ml. With large increase in GFR and plasma glucose concentration that increase the filtered load of glucose above 375 mg per minute, the excess glucose filtered is not reabsorbed and passes into the urine. Relation between plasma concentration of glucose, filtered load of glucose, further transport maximum of glucose, and rate of glucose loss in the urine can be very important. Note that when the plasma glucose concentration is 100 mg per 100 ml and the filtered load is at its normal level 125 mg per minute, there is no loss of glucose in the urine. However, when the plasma concentration of glucose rises above about 200 mg per 100 ml, increasing the filtered load to about 250 mg per minute, a small amount of glucose begins to appear in the urine. This point is termed the threshold for glucose. Note that this appearance of glucose in the urine at the threshold occurs before the transport maximum is reached and represents display in the otherwise linear relationship between plasma concentration of glucose and the submaximal tubular transport of glucose. One reason for this difference between threshold and transport mechanism is it is not all nephrons have the same transport maximum for glucose, and some of the nephrons before begin to excrete glucose before others have reached their transport maximum. The overall transport mechanism for kidneys, which is normally about 375 mg per minute, is reached when all nephrons have reached their maximal capacity to reabsorb glucose. The plasma glucose of a healthy person almost never becomes high enough to cause glucose excretion in the urine, even after eating a meal. However, in uncontrolled diabetes mellitus, plasma glucose may rise to high levels, causing the filtered load of glucose to exceed the transport maximum and resulting in the Urinary glucose excretion. Some of the important transport maximums for substances actively absorbed by the tubules are as follows, like glucose 375 mg per minute transport maximum, phosphate 0.10 mm per minute, and lactate 75 mg per minute. And calculation of tubular reabsorption or secretion from renal clearance. If the rates of glomerular filtration and renal excretion of a substance are known, one can calculate whether there is a net reabsorption or a net secretion of that substance by the renal tubule. For example, if the rate of excretion of the substance is less than the filtered load of substance GFR into PS, then some of the substances must have been reabsorbed from the renal tubule. The following example illustrates the calculation of tubular reabsorption. Assume the following laboratory values for a patient were obtained. Urine flow rate 1 ml per minute. Urine concentration of sodium UNA is equal to 70 m equivalent per liter. Then plasma sodium concentration 140 m equivalent per liter. Then GFR inulin clearance 100 ml per minute. In this example, the filtered sodium load is GFR into PNA or 100 ml per minute into 140 mu equivalent per ml. Why mu equivalent? In the sense urine concentration of sodium, we have learned UNA is 70 m equivalent per liter, which can also be stated as 70 mu equivalent per ml. So we will be multiplying that 100 ml per minute into 140 mu equivalent per ml. We get 14,000 mu equivalent per minute. Urinary sodium excretion UNA into urine flow rate is 70 mu equivalent per minute. The tubular reabsorption of sodium is the difference between the filtered load and urinary excretion, or 14,000 mu equivalent per minute minus 70 mu equivalent per minute is equal to 13,930 mu equivalent per minute. Conversely, if the excretion rate of the substance is greater than its filtered load, then the rate at which it appears in the urine represents the sum of the rate of glomerular filtration plus tubular secretion. Then the secretion rate is the difference between the urinary excretion and the filtered load.